Please switch off your mic because I am going to tell. If any doubt, you please ask. After 3-4 slide, I can ask you. You can we can discuss. Okay. Okay. Okay, so static timing analysis. This we'll discuss about static timing analysis. Mostly, these are this type of analysis we carried out to find out whether there are any timing violation in digital circuits, in digital system design. And we know that most of the designs are synchronous. So mostly all these analysis are carried out for a synchronous design. And followed by, we also know 60 to 70% of designs in a system are digital design. So mostly that's why we called it as RTL level design, register transfer level design. So registers are there. So when registers are there, clock is there. So flip-flop will be created. So between two flip-flops, and we have to verify that whether it is maintaining the timing analysis properly or not. So it's all about, like, you just assume that your entire design is divided into. Please switch off your mics. Your entire design is divided into combination of paths, or you can say data paths, and you can say timing paths. So in timing paths, there will be many flip-flops. In between flip-flops, there will be combinational circuit. So what static timing analysis generally does is it will try to see or try to see that all the timing between available paths are fine or not. Okay, so I have told you in previous classes there are two types of timing analysis happens. One is called static timing analysis. So this is actually STA is performed in two ways. I have written, but it has to be corrected. It's something like timing analysis is performed in two ways. One is called static timing analysis, followed by dynamic timing analysis. In my previous classes, I told that dynamic timing analysis, where the we in the x-axis timing will be there, and we used to give inputs and observe the outputs, and we have to observe this input output combination or the functionality of the design is correct or not. We used to do this with respect to time. Okay, so time is being changed in the x-axis, so that's why it is called as dynamic. Time is not fixed here. Okay, so that's why that is called dynamic timing analysis. But dynamic timing analysis is always corresponds to something like checking about the logical functionality of your design. Your time advanced in x-axis, but in the meantime, you are checking always that your functionality is correct or not according to your requirement. Okay, according to your specification of the design. Okay, so in contrast to static timing analysis, uh, it does or it works in a different way. So what we have written here, static timing analysis is a method of validating the timing performance of a design. Okay, so by checking all possible paths for timing violations under worst case conditions. So that means under there will be various design paths, timing paths will be there, and timing paths means there will be various flip-flop and there will be some path connected between these flip-flops. So when data is traveling from one flip-flop to another flip-flop, so that path is called as timing path. Okay, so we have to see all the possible timing paths, and we have to check that whether there is any timing violation. So what do you mean by timing violation? Because if you want that flip-flop, let's say flip-flop 1 and 2 are there, and flip-flop 2 should get it data, let's say at 10 nanosecond. So whether the data reaches there at 10 nanosecond or not, That is what our requirement. Okay, if it is not reaching at 10 nanosecond, then it is violating the requirement of the flip-flop 2. Okay, so there are various factors like setup time, okay, so when we are doing timing violations, right? So that's why static timing analysis is a method of validating the timing performance of a design by checking all possible paths for timing violations under worst case conditions. So worst case condition means you have to check all the conditions. It may be best case or worst case, means in it may be a single path, it may be multi-path, or whatever paths are there, you have to check for everything, and you have to see that all these conditions are working fine. Okay, it considers all worst possible delays through each logic element. Okay, so there may be a chance that net delays may be classified into two times. Sometimes you will have maximum net delay, you will have minimum net delay. So like that, it is characterized. Okay, so in that case, it will check all possible combination of delays in a design, and it will try to observe that whether there is any timing violations between the all possible timing paths. Okay, but it is also simultaneously, you have to note that it doesn't check the logic operation of the circuit. Okay, so what we'll check is, we'll have flip-flops, we have to check whether it is meeting setup time, hold time or not. We will never try to see or understand what the design is doing. We will not check the functionality of the design. Okay, so in comparison to other methods, static timing methods are faster, and more thorough. Okay, because when you are checking only operations or functionality through dynamic timing analysis, so the best way is that you have to give all possible input combinations and you have to check the output by chance, and which is sometimes a tedious thing. Okay, but there are lots of other methodologies are there, like system verilog and other verification methodology. But sometimes in order to check the entire design for the functionality correctness, you require more time. Okay, so that's why so if you want to sit and finalize your timing analysis to only DTA, so it requires time. But at the same time, in static timing analysis, what happens? It gives you a more thorough checking of the timing violations in a design, and at the same time, it performs the operation in a faster way. Okay, you no need to check all the possible input combinations against the corresponding output, desired output. You have to just check all the flip-flops and its timing violations. Okay, so here it is written one again. Note this. It is very important that static timing analysis checks the design only for proper timing, not for correct logical functionality. Right. Okay, so static timing analysis seeks to answer the questions like, will the correct data be present at the data input of each synchronous device when the clock edge arrives under all possible conditions? That means you have to just verify that if there is a positive edge trigger clock, so if clock arrives, whether your data is there or not. Okay, so if it is there, then it is not violating the your timing analysis. Okay, so that is what we do here. We have to answer the questions like, will the correct data be present at the data input of each synchronous device when the clock edges arrive? So all these things, or all these types of questions, we generally ask during analyzing the timing through static timing analysis. Okay, all these things we don't discuss when we do dynamic timing analysis through writing test bench and all. Okay, so how STA is performed for a circuit? So the STA is performed by using three main steps. One is called, first step is you have to break entire design into set of timing paths. So you have to find out how many flip-flops are there, how many connecting flip-flops are there through which the data is traveling from input towards the output. Okay, so it may be one, it may be multiple, but you have to find out all the timing paths. Then second, calculates the signal propagation delay along each path. Okay, and third, and checks for violation of timing constraint inside the design and the input output interface. That means uh, there will be first you have to break the entire design into various timing paths. So each path may contain say data traveling from one input flip-flop to, or from one flip-flop to another flip-flop. Okay, then you have to find out the entire propagation delay or entire delay between the input data sent till the output data received. Okay, after that, through each flip-flop in that path, you have to verify the timing constant. Timing constant means you know what is the setup time of the flip-flop, what is the whole time of the flip-flop. So you have to verify when the data is traveling, it is matching the requirement of each flip-flop's setup time and hold time. Okay, and also at the same time the timing constraints also related to your design, because when you are designing any system, so you have to verify that your data when it is traveling from flip-flop 1 to flip-flop 2, it should reach at this particular time. Okay, so if that time is met, then you don't have any violations and you it will pass the static timing analysis. Okay. Okay, so this is about one in the small introduction about STA, and actually, truly speaking, all the slides from here I have taken, I have star marked. There is a site called vlsi-expert.com. This is actually a blog site maintained by one person. So perhaps I met him in some meeting at Kharagpur, perhaps. I don't know exactly because the name I found later I didn't get it, but but anyway, when you will start searching STA related queries and questions and documents in the internet, you will find this site as very useful. Okay, so I have taken few times long 3-4 years back to understand the concept and to discuss with all of our students so that it will be very helpful to them. So all the theory, the matters is belonging to this side. Okay, and followed by there is a book called Static Timing Analysis by J. Bhaskar, the same author who has written book for Verilog. So he has written many book on VHDL, Verilog, System C, System Verilog, and also finally you will find another book called Static Timing Analysis. So that is a bit theoretical approach, but he has written a book on this. So you can just imagine how vast the thing is. But anyway, I will try to cover a few important aspects within these two classes, and few doubts will clarify so that you will at least get a domain and minimum expertise, and again and also a triggering point. From here you can start on your learn on your own to learn the things and again deliver to your friends or somebody so that you can learn in a better way. Okay, so when, frankly speaking, or truly speaking, you may have a doubt in your mind that in digital design like mobile, SOC and all, so there are lots of timing paths will be there. There will be lots of flip-flop and there will be lots of timing paths. So that's why it is not manually possible to solve or not possible to analyze each path by manual operations. Okay, so that's why what happens, sophisticated and advanced CAD tools are developed. So one of such tool is called Prime Time, which is mostly by Synopsys company. Similarly, Cadence, Mentor Graphics, they are having their own timing analysis tools. So prime time you will find very heavily used in industry. Okay, so what these tools does actually, the STA tools analyzes all the paths from each and every start point to each and every end point and compares it against the constraint that exists for all the paths. Okay, so you have to give the design clock period to the, you have to give the clock period of the design, what are the timing characteristic and timing constraints to the design during your synthesis of your design. Okay, so by taking this design constraints, So prime time synthesis tool will create a get level netlist. So that I told you. So it may be in Verilog or VHDL, in any form you can save it. So once it is done, that get level netlist is given to prime time tool or any timing and static timing to analysis tool. They don't take the RTL code, because RTL codes are like a soft code, like a virtual code. They doesn't actually replicate any library. But I told many times that when you are doing synthesis, the synthesis requires two inputs. One is called your RTL code, and second is your vendor library specific files. Okay. So when vendor library specific files are given, so what synthesis does, actually I told this many times, synthesis tool take the RTL code and it will try to map the corresponding gates, flip-flops, muxes to the corresponding gates, flip-flops and muxes available in the vendor specific library files. So here vendor is the company with whom you are going to fabricate your IC. Okay, so if the vendor, let's say any company, so they will provide you the technology in which you are going to fabricate your IC. Let's say a very standard academically used technology is 180 nanometer. So that refers to your transistor length. Okay. So L size, which is fixed over your design, and W will vary according to your design requirement and calculation. Okay. So once, depending upon this W by L ratio, a set of libraries are created which consists of standard cells. Okay, so these standard cells may be for AND gate, XOR gate, mux, various types of flip-flops. So all these standard cells are being designed, and in form of a library, vendor will provide to the designer. So designer will take all these libraries for a specific technology, like say 180 nanometer. So libraries are specific only for the technology. So if you are you want to design anything in 28 nanometer, then you have to sign an MOU and take the corresponding library for 28 nanometer. Okay. So vendors are taking all these libraries for a specific technology, and they are giving to synthesis tool. Means vendors are providing this, designer is taking all these things and they are giving to synthesis tool as input. They are giving design constant, timing characteristics, what you require for that particular design, and also they are giving RTL input. Okay, RTL Verilog file or VHDL file as a coding input. So after this is over, synthesis tools are designed in such a way that it will replace all the virtual gates available in the RTL code, and it will map with the gates available in the library. Okay, so at the end of synthesis tool, you will get a gate level netlist. So these gates are, you can say real gate, because the library, whatever provided by the vendor, they provide the gates with various characteristics. Like if it is a combinational design, they will provide with its propagation delay. If it is a flip-flop, they will give the setup time, hold time, and also they will give power of the gate or flip-flop, what power it is consuming, what area it is consuming. Okay, so that's why you can just imagine this get level netlist, which is again in SDL, VSDL or Verilog, is different from the RTL code, which is again in same VSDL and Verilog. Okay, so these get level netlists, which are, when you will compute, it will give you how much power it consumes. Okay, what is the area it will give you. So all these things basically we do in FPGA, but these are very much being done in the ASIC level, IC design level. So static timing analysis, what I am telling, it is also useful in IC level designing. Okay, so in next semester ASIC lab design, they you will perform this ASIC implementation steps. So at that time, you may see how the synthesis is done, what is the area. After synthesis over, you can see the area, you can see the timing, you can see power. Okay. So once the gate level netlist is done or it is with you, that gate level netlist is fed with timing constant to the prime time types in timing analysis tools, and those tools used to perform the timing analysis. Okay, so while performing the timing analysis, they used to find out all the possible paths, and they used to check whether all the possible paths are meeting their timing requirement or not. Okay, so it is not like you have to sit and do everything on your own, sitting at your office or in your laptop. It's not possible because today's system becomes very complex. Okay, so you will find in 1 lakh or 1 crore of transistors inside this. Okay, so that's why corresponding tools are being developed perform properly in both means you can analyze it in each path individually, and you can perform the timing analysis through a sophisticated tools, okay, or advanced tools. Okay, so now coming to next, so first concept here is called as setup time and hold time, and I assume all of you know a setup time and hold time. I will just read out and then summarize this slide. Okay, so now as you can see the below figure, the clock is a positive edge trigger and clock is advancing. C is the clock. It is advancing from 0 to 1. So that's why it is a possess type clock. And here if you'll see there is a D. Data is the D is the input. It has changing. D is changing actually. Okay. So the non-shaded area is portion which is beyond your TSU. TSU here T setup time and THD here is the T hold time. Okay, so yeah, we know that setup time is the time, that is the minimum amount of time the data signal should be held steady before the clock event. Okay, so that data are reliably sampled by the clock. So you can assume that if this there is a trigger arrow is here. Okay, so setup time is the time that when data or D is continuously changing. You can see in shaded area D is changing. Okay, it's not stable, but when it is reaching to the TSU area, so it is assumed that the data is stable now. So the requirement of setup time is that it is the minimum time amount of time from which the data must be stable. Okay, so that when clock edge will happen, it can properly trigger the data. Okay, or latch the data. Okay, so this setup time is a synchronous time concept. It applies to all the flip-flop, or in short we can also say that it is the amount of time the synchronous input D must be stable before the active edge of your clock pulse. Okay, understood. Similarly, hold time is the time or is the minimum amount of time the data signal should be held steady after the clock event so that the data are reliably sampled. Okay, what it means is once the data is stable at T setup, then at the aging point or triggering point, a clock triggering point, data will be last or it will be sampled. But after when you are reaching the hold period, after the soon after the data is sampled, your data input must not change. It should be stable for another period, which is called T hold period. Okay, so that's why the name is hold. So data should be stable before, so it should be set up properly before the setup time, or at least at the minimum setup time. Then after that, data should be fixed. There should not be any chance that this data is overridden by some other input data. So if it is overridden during the whole period, then the data will become garbage. Okay, so that is the concept about your setup time and hold time. So in for hold time, in short, we can say that the amount of time the synchronous input D must be stable after the active edge of your clock pulse. Okay, so that this is about setup time and hold time, and this concept you know from your digital electronics classes. So now we'll see what is setup violation and what is hold violation. So if you will take only one flip-flop and you will try to understand setup violation and hold violation, sometimes it is not possible. So if you will take two flip-flops, then we can understand what is setup violation and what is hold violation. Okay. So now you can see most of the time in your design, the timing paths will be consist of two flip-flops. There may be many flip-flops, but mostly if you will divide and on into small part, if you divide all the design into small portion, then you will find at least there will be one flip-flop one. Okay, and there will be some combinational circuit in between where your actual computation will happen. After that, so first it will be flip-flop one, then there will be combinational design, then after that there will be flip-flop two. Okay, so we have to check in this both flip-flop that when the data is traveling from input towards the output within a synchronous design, whether the timing is correct or not, whether violation is happening or not. So as the name indicates, setup violation and hold violation. So in simple manner, I can say if your data is not stable during the period of TSU, then it is setup violation. Or if your data is not reached at this point, or even if after reaching it is not stable, then that is also setup violation. Similarly, if your data is triggered, after that the data must not change till the whole period. Okay, if you are changing it or by any means your input data is coming and it is not maintained proper with proper timing, and you are just changing or overriding this old data, then that is called as hold violation. Okay, so if setup is not met, it is setup violation. If hold is not met, it is hold violation. Okay, so here we can say few important things to note down. First is you can see there are two flip-flops are there. Within that there is a combinational design which will do because flip-flops are there to latch, but combinational designs are the paths within the, or you can say is a functional units which is responsible for doing the computation. So this is a basic figure which replicates your entire timing paths in the systems. Okay, so we'll study and understand these violations and mitigation of violations with respect to these figures. Okay, so the important thing to learn, thing to remember here is data is lunch. So you can see FF1 has C as clock, D as input, Q as output. Similarly, FF2 has C, D, Q respectively. So timing path is given. It's starting with a from C to Q with a dotted arrow. Then it passes through the combinational logic. Then it reaches to the D input. So this is called as one timing path. Okay. So when the clock is there and this data reaching at D input should reach at minimum setup period before. Okay, then only that, and it should be stable. And after reaching, if clock is positive phase triggered, the triggering is happening, then it should say value should not change. It should remain same. Okay, during this period. Okay, so that is what called as timing analysis. Okay, so so here there are two things are there or to remember. So first is okay. So first thing is like data is launching from flip-flop 1. So data is launching from flip-flop 1D to flip-flop 1Q. Okay, at the positive edge of your flip-flop 1C. Okay, then at FF2D input data is coming from FF1Q through a combinational logic, and data is captured at FF2D at the pulses of the clock of FF2. Okay, so we can say that launching flip-flop is FF1 and capturing flip-flop is FF2. Okay, so are you getting? So this is the most of the time you will find similar scenario where there is a flip-flop 1, then a combinational logic, then a flip-flop 2. So what data you are pushing in the input, which is the main input, which is the flip-flop 1 input, should go to the main output in this design, which is the output of the flip-flop 2. Okay, So in this process, we have to check that the violation should not happen for setup time or hold time. Okay, so when the data is given in the FF1, it is actually captured at poses of your clock pulse, then it passed through the combination logic, then it reaches to the D input of the FF2. Again it is captured at the poses of your clock of the FF2. Then again the data is captured and propagated to Q output. That is our final output. Understood? So that's why the whatever data you have sent at the input of the FF1, it will be finally captured at the output of the FF2. Okay, and then only your one operation is complete. Okay, and that's why we can say the launching flip-flop is FF1 and the capturing flip-flop is FF2. And the timing path here is starting from FF1C to FF1Q, then the FF2D. Okay, followed by in between combination logic is also there. So if there is a delay in the proper combination logic, so this delay will also add up while calculating the final delay till FF2D. Okay, so now we have to summarize a few important things from here. So first thing is you see the below clock. So clock FF1 and there is another clock called clock FF2. So as it is synchronous, so this is both are same. Okay, but the period of these clocks are 10, let's say 10 time units. Okay, so clock FF1 at 0 time units, assume that I am giving a 0 at clock. Okay, assume that at 0 time units the clock is on, that is it's becoming positive as trigger. Okay, so at that time assume your data D is here. Okay, input data is available at the D. Okay, so that data at 0 time units it will be last and it will go in fast clock pulse to the input of the combinational logic. Are you getting? At 0 time units this will happen. At the same time of the 0 time units there is no data latching in FF2 because the data yet not reached to the D input of the FF2. Okay, now in the second clock pulse, that is at 10 time units, what will happen? The input, the data which is reached at the Q output of the FF1, passing through a combinational logic, it will reach at D input of the flip-flop 2. Okay, so here it will be captured at 10 time units, which is poses of your clock. Okay, and that data will go to the main output of this design. Are you getting? So this operation will happen in this way. Okay, so now we have to correlate. If this operation is happening in this way, then how we can observe what is setup here, or what is say how to measure the setup violation of this data here, setup violation of the flip-flops for a specific input passing from FF1 to FF2. How we have to analyze that? So what is setup and hold violation with respect to this particular input and this design? Okay. Okay, so that's I have written in the red color here. So for a single cycle circuit, signal has to be propagated through the data path on one clock cycle. Okay, so means if data is launched at time 0 nanosecond, okay, from FF1, then it should be captured at time 10 nanosecond in the FF2. So in by 10 nanosecond, the FF2 should able to capture the time. Okay, so that's why your period will be then 10 time nanosecond. Your clock time period will be 10 nanosecond. Okay, so this is about this setup analysis and what is old analysis in. Okay, so now you check. So assume that. So when you are doing setup analysis, so for setup analysis at FF2, data should be stable at TS time before the poses of your FF2C. Okay, that means what I want to say is, so your data is traveling to FF2. So when it is traveling to FF2, there will be a setup time for FF2. So let's assume that this setup time is TS. Okay. So data is from where the data travel? Data has traveled from the input of the FF1 or D input of the FF1 at 0 time units. That is the fast clock causes of your input. Okay, at 0 time units. Okay, now for checking the setup time whether it is meeting in FF2 or not, what you are doing, the data has traveled to at 10 time units. Okay, so to observe that your setup is not violated, what you have to do is you have to check that the data should reach before TS time of the 10 nanosecond at FF2 flip flop. But okay, so data to FF2 flip flop before TS time. Okay, so that's what I have written. I am just reading out so that you will get clarified. So setup time analysis at FF2 is so that if you are doing setup time analysis at FF2, the data should be stable TS time before the poses at FF2C. Okay, so where TS is the setup time of the FF2. Okay, next is if assume that TS is 0 nanosecond, it's a ideal case setup time is 0, then data learns from FF1 at time 0 nanosecond should arrive at D of FF2 before or at 10 nanosecond. Are you getting or not? If data takes too long than 10 nanosecond, then it is called as setup violation. Okay, if assume that my TS is 1 nanosecond and data launched at 0 nanosecond must reach at FF2 before 10 nanosecond minus 1 nanosecond, that is at 9 nanosecond, in order to meet the timing requirement, then only the setup violation is not done. If data is reaching after 9 nanosecond or beyond that, then setup violation happens. Are you getting? See, let us, it is not a simple thing to understand, though we read all this thing in setup time, hold time in digital electronics. I don't know how much emphasis mostly it is given at that time to understand all these things, all the things. So we should have a minimum interaction somewhere. Okay. So I want to ask that whether all of you got through this two bulleted paragraphs of this slide, or any doubt, then we will discuss. So assume that we are just checking everything with respect to 10 nanosecond now, because my data is launched at 0 nanosecond at the input of the flip flop D of the FF1, and that data is traveling from the combinational logic. It is reaching at the D of the FF2 at 10 nanosecond. While because in fast there is no data, when data is reached here, at that time clock advances to 10 nanosecond. So at 10 nanosecond, I have to check what is the setup time of the data available at the D input. Okay. So if my setup time is 1 nanosecond, the data must go 1 nanosecond before, that is 9 nanosecond, 10 minus 1, 9. So at 9 nanosecond, the data must be present and it should be stable. Then only it will not violate the setup timing, or setup violation will not happen. Are you getting? So means what I want to say in this diagram, let's say this mid one is 10 nanosecond and my setup time is 1 nanosecond. So this dotted line left side from top to bottom is 9 nanosecond. So data must be reached at 10 minus 1 9 nanosecond and should be stable here before the 10 nanosecond happens. That is your triggering point. Okay, similarly for hold evaluation, once the data is triggered, it should be hold for another 0.5 second. Assume that let's say my TSD is 0.5 second. So data should be stable from 9 to 10.5 second nanosecond. Are you getting my point? then only we can say that there is no setup violation or there is no hold violation. If your data is reaching after 9 nanosecond, then there is a setup violation, or your data which is hold up to 10.5 second, whether it is changing in between this, then that is called as hold violation. Okay, are you getting this? You have to clarify me, then only I will go ahead.
Yes, sir.
Yes, sir.
All of you?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So in fast, what is written? They have assumed setup time is 1 nanosecond. In hold time analysis, they have assumed hold time is 0.5 nanosecond. Okay. So data must be stable from 9 nanosecond till 10.5 nanosecond. And if it is ideal, then data must be there at 10 nanosecond fixed. So T0 indicates it's an ideal case, TS0 or T hold 0 indicates it is an ideal case, and data must be present at 10 nanosecond. But ideal case is really actually not possible. So whatever setup time is given, so from the clock period, you have to subtract that like 10 minus 1, then from 9 nanosecond your data must be present and it must be stable. Okay, and after triggering is done, after 10 nanosecond plus the whole time, let's say 0.5 nanosecond, so till 10.5 nanosecond, from 9 to 10.5 nanosecond, the data must be stable. Okay, then only it is assumed that data will be latched properly and it will be further utilized in the further designs, means your subsequent path. It will not be overwritten. It will not become garbage. Okay. So now what we conclude out of this, see, when the data is launched at the launching flip-flop, okay, are you getting? So the setup is checked in the capturing flip-flop. That is next flip-flop. Okay. So when the data is present or it is sent from the launching flip-flop, the setup is checked in the next flip-flop, not in the same flip-flop. Which data you are sending in this particular design, which data you are sending, when it is reaching in the next flip-flop, at that time you are checking whether the data setup or whether the setup time is correct or not for the corresponding FF2 flip-flop. Are you getting? That's why we have written with the above explanation, we can say that two important points. One is setup is checked at the next clock edge. Okay. Similarly, hold is checked at the same clock edge. Why? Because when the data comes here at the FF2, we are checking that while after latching, it should be hold same or stable for a certain period. Okay, so you have to remember these two observations and two important observations. One is mostly between two flip-flops when data is sent and received or data is transferred, the setup is checked or setup violation is checked for the at the next stage of your clock pulse for the next flip-flop, and hold is checked at the same edge of your clock pulse for the next flip-flop. Are you getting? So this you have to again, if you are not getting, please go through tonight's. If any doubt, tomorrow class we will discuss. Okay, so that's why these arrows are given. From one clock pulse, it is launched in the second. When it is captured, the setup is checked. But after capturing, hold has to be checked. So that's why hold is checked in the same clock pulse. Okay. Next is the same thing they have tried to show you in a detailed way, like the same diagram in the left side and right side another diagram, timing diagram, to observe that what is happening actually. And also from here three important terminology of the timing analysis will understand. Okay, so in the above figure we can see that the data launched at FF1D. So there is a clock here. So launching edge is this pulses of your clock, first one, and in the second pulses of your clock is the capture edge. of the flip-flop for this particular design. Okay, so data is launched at FF1D. Okay, that is at launch edges and reaches to FF2D. It passed through the combinational logic delay and reaches as FF2D after certain delay. Okay, so that delay is equal to CLK to Q delay, clock to Q delay plus combinational logic delay. That is your this delay. So after this two delay is over, your data is reached at D. So that's why you can see here launch is pointed an arrow and data is launch here. So when data is launch before to this clock, also we assume that data is stable. So he has shown the data is stable before this period and it is changing from 0 to 1 and again finally from 1 to 0. Okay, so you can see CLK to above to this the third waveform, below to top, from bottom the third waveform. You can observe the delay happening due to clock to Q delay and also the clock to Q delay of the FF1. Are you getting? So after that, again there is a combinational delay. We assume that there will be many various circuits in the combinational path. So combinational delay it has taken as a more than CLK to Q. So combinational delay is happening. Then data is arriving at the input of the FF2 at the capture flip-flop in the fourth figure or fourth diagram from the bottom. Okay, but actually capturing edge is data capture event at FF2. Okay, so now here three things you have to remember. One is called arrival time, one is called slack, one is called required time. Okay, so required time is the time where the data must present and it should be stable. Okay, so that's why it is like the clock edge minus your setup time is called your required time. So that you can see this red marked area arrow pointed is flip-flop FF2 setup time requirement. Okay, so during this period the data must be present and it should be stable. So that is called as required time. Okay, but in this design we have seen is your after the combinational delay the data is available much before to this. So that is called as arrival time. So required time is the time after deducting from the clock edge to the setup time. This is the actual time where the data must come. That is called as required time. But what happens many times there may not be that amount of delay in the data path. So data may arrive before to this, and that is called as arrival time. Okay, but anyway, this arrival time is beyond or before to required time. So that indicates your system is or your violation is not there. It is already stable before your required time. Okay, so this arrival time and required time, if you subtract, you get one term called as slack. So slack is calculated as, you can see below, required time minus arrival time. Okay, so if it is positive, like required time is let's say 9 and arrival time is 8, then 9 minus 8 is 1. So if it is positive, then there is no violation. Okay, but if this delay will come or it will, then delay is more in the combinational path and it is happening after your required time, then if you minus required time and arrival time, it will become negative. Okay, it happens due to the delay. If there is no proper timing is or design is not done, combinational logic, after the combinational logic delay, the data is available after required time, then required time minus arrival time will become negative. So at that time the slack becomes negative. Okay, so if slack is negative, then there is a setup violation, and if slack is positive, then there is no setup violation. Okay, so see what I will do is as there are classes for others, few students, so we'll end it here. Okay, and what
Sir,
I am just huh.
sir, class got cancelled, sir. That class.
Oh, so all of you are free. I can take another 15 minutes. Okay, all of you are free, right?
Yes.
Okay, so now did you get what is slack, what is arrival time, what is required time? So you can just say data capturing clock period minus setup time is called your required time. So this is the required time which is fixed. Okay, and all should meet this time. If your data is coming before to this, then that is slack is positive because slack is equal to required time minus arrival time. If it is positive, then it's fine. Data is already present beyond your required time, and the clock capture in at capture age, clock can capture it. Okay, but if it is negative, that means it reaches after your required time. Okay, just assume that your required time is, let's say, 9 and arrival here is, let's say, 8. So 9 minus 8 is 1 nanosecond. So it is positive. It's available earlier to this and slack is positive. Then there is no violation. Just assume that it is 9 nanosecond and data reaches after 0.5, like let's say at 9.5 nanosecond. Means your required time is 9 and arrival time is 9.5. So the result is how much? Minus 0.5 less than 0. So it is negative. So in that case, set of violation. Okay. 1 second. Okay. So did you get it? So this is one important aspect is called as slack, which is related to your required time and arrival time. Okay. So when timing analysis is done by using prime time or similar prime designs, so what they do actually after each timing calculation for each timing path, they give the slacks positive or negative. So if you will find so and it does automatically. So you give the things design constant, clock, timing constant, and get level input to your prime time tool. It will give you which slack is positive, which slack is negative. So that individually you can go and you can observe the individual. Then you can point to that particular path and you can do manual calculation for that path. Okay. So if you find out of 10, like 8 are positive, then no need to worry. Only those two which are negative, you have to worry about that. Okay. So this is where the slack is plays a very important role, right? Then there are certain description about delays. So this thing you know. So in a short, I will tell. So one is called your rise time, fall time. Then there is a delay like TP. So that is low to high pulse delay and high to low. So it's something like you can say when your rise time is the transition of the signal from 10% to 90%, and fall time is the signal transition from 90% to 10%, and propagation delay, which is average of TPLH and TPHL, is the delay measured between one input to another in output. Okay, when it reaches from 50 means when the input is 50% and output is 50%, at that time you just find out that will be your propagation delay. Just see here, rise time is related to zero point 0.1 to zero point 0.9 and fall time is related to zero point 0.9 to zero point 0.1. This also you know, but when the propagation delay is coming, when the input, this is a buffer, so your input and outputs are waveforms are same, but you can see when input is 0.5% of Vmax and output is also 0.5% of Vmax, at that time the difference is called as TPLH because your output is transiting from low to high. So that's why it is called TPLH. Similarly, in the right side, output is transiting from high to low. So that's why 50% of input and 50% of output, if you will check, it is called as TPHL. Understood? So this is the same concept, but what we want to see that what do you mean by propagation delay in sequential circuit? Okay, so when it is combinational design, at that time propagation delay is something when the delay is transferring from input to output. Okay, so that you can see if this is a combinational input, like buffer combinational design, your data travels from input to output from X to Y, whatever delay incurred, that is your propagation delay. Okay, but in case of flip-flop, you can see there are two paths. One is the data is present at D, it wants to go from D to Q. So there is certain time required for that. Okay, at the same time, it should launch or it should be done. The data D will go to Q when there is a time from C to Q. That means there is a clock period is there. So if that C to Q is whatever time is there, when that met, then only the data D to Q will transfer. That means here in combination, the propagation delay of sequential circuit can be divided into two parts. One is the data D to Q, another is from C to Q, but priority is given to C to Q. That's why I can say when you are writing Verilog code for a synchronous design, you always write always at the rate of process of clock. You don't write there at the rate comma D. Understood? As D is one of the input, even though we don't write always at the rate of process of clock comma D. We only write always at the rate of process of clock. Data output is equal to data input, means Q equal to D. Okay, so that is why what we want to explain here, we have tried to explain here, the in the combinational circuit every timing characteristic of parameter are with respect to the data input change, means it's event trigger, so whatever input change output will change, but depending upon the propagation delay. But in the sequential circuit the change in data input is important, but change in clock value has the higher precedence. Example, in a process of triggered flip-flop, the output value will change only after the presence of the process of clock. Whether the input data has changed long time ago or not, it doesn't matter. Only thing matter is when the process of the clock is happening. Okay, so flip-flops only change value in response of the change in the clock, not in the response of change in D input. Timing parameters, when you are specifying, we specify with respect to pauses of positive edge trigger or negative edge trigger. Okay. Now, in the same context, he has tried to again explain that setup time and hold time of a flip-flop, which already we discussed. So I don't want that we'll discuss here. So you can see in CLK, the pulse width is TW, you know this. And before to pulse width, the minimum time through which the data must be stable. That is clock at TSU, that is T setup. And after this clock triggering, process of your clock triggering, after this T hold period through which the data must be stable. That's why D is stable from TSU to TH. Okay, it's not stable in this period, then setup and hold violation will happen. So if it is stable, that is called as means you can say violation free circuit. Okay, timing violation free circuit. So now that this period is all time, then TPLH is the period when your data input, when the data is changed after your hold is done. Okay, so at that time it's becoming low to high, and whatever period it is taking. See here, what he wants to say is in the D flip flop. Okay, the TPLH will be calculated with respect to the clock, not with respect to the D flip-flop input. Is what we want to point out here. If this is a buffer, so TPLH is calculated with respect to input of the D at X, okay, and 50% of that with respect to output 50%. But when it is coming to clock circuit, it doesn't matter when the D changes, the output changing from low to high or TPLH will be calculated, or propagation delay will be calculated depending upon the triggering of the clock. Here it is positive edge triggered clock. Understood? So this is what I am doing is, actually I need to stop here because I have one appointment somewhere. So again tomorrow we'll meet at 11 a.m. Okay, I will start the class. If by chance I want all of you come, if you will tell, if somebody is not copying, anyway I will take the class, and recording will be there so that you can understand it. So let us stop it here. And what I am doing is, in the meantime, I am sharing this slide in this group. So if you possible, please go through all these slides. And tomorrow when we'll meet, it will be easy for you to understand. Okay. So uh, let me take the attendance, then you can leave. And tomorrow at the same time again we'll meet. I